Hi there, I'm Mike Glass with Orion Technical Solutions. Today I'm going to talk about an interesting process control problem that I ran into a while back. I'm going to present some questions in there and I'm going to provide some answers with some context later in the presentation. To make sense of the question, you're first going to need to understand the basic system. So the system in this example involves a process you're controlling the upper ranges of a surge tank. There's other controls for the bottom end, but we're just looking at the top end for now. Basically, if the inflow coming in here exceeds the outflow, then the level would rise over time, obviously. So what we do is we have two control loops that are going to discharge product overboard to maintain a balance between the raw influent and the effluent. The small valve, which is in this case LCV 652D, it's set up for 1 to 20 gallons a minute, roughly. The big valve is set up for 10 to 200 gallons per minute. That's LCV 652E. So in the controls, they basically tried to set this up. Well, the functional description that is what programmers are supposed to use to develop their code and so forth. The functional description for this process says basically that the small valve will dump a portion of the incoming product overboard to prevent the level from exceeding 54 inches, and it should be full open at 78. So it basically should start opening at 54 and be full open at 78. The big valve should dump a portion overboard, same thing, to prevent level from exceeding 72 and should be full open at 84 inches. Now granted, that's literally some pretty precise wording and it's not the best wording, but that's the kind of wording sometimes you get in a specification or in a functional description. But that is not what was actually implemented, and we'll talk about that. So in the real world application, the system was set up with two control loops, and the settings were shown. Basically, we have two control loops, and as you look at that, you can tell they're both proportional and integral. They both have proportional and integral. No derivative here, but there is integral action on both of them. And they both have two distinct different set points. You'll probably notice that those numbers are kind of the middle of that range that was spelled out in the functional description. We'll talk about that later. It also helps in analyzing the question I'm going to ask if you know some of the insight. Both of these loops individually are tuned fairly aggressively for what they're intended to do. So here's the questions. The first question, what's wrong with the system that's implemented and what will it actually do wrong and why will it do that? The second question is, describe a better solution for this issue, and ideally one that is in accordance with the functional description. There's actually lots of ways to solve this problem. To keep that straight, we'll try to solve the actual functional description, which actually can work pretty well. The third question is, how or why do you think this problem came to be? And a hint in this case is that this happened way before commissioning. And that's how it often is. So we'll want to talk about that because ultimately that's what we're trying to do here is solve problems, prevent problems, identify problems, and knowing where they start is a big important part of it. So having multiple controllers try to manipulate the same process variable, level in this case, is going to cause them to compete for control. Let's analyze this a little bit. This is a lot like having two children assigned to put the same toy in two different bedrooms. There's going to be a tug of war. it can't be in two places at once. It can't be at two set points at once. So in this process, when the raw influent was less than about 10 to 20 gallons a minute above the effluent, the small valve, LCD 652, will control the process. And it'll maintain level at the set point for LIC 652D, which is 66 inches. But when the raw influent is about 20 gallons or more above the effluent, so we got a lot more inflow now, the small valve is saturated. It's fully open. And now the large valve really obtains control. It's the one that can modulate or has any impact on the process because the small valve is fully open. So the large valve, that LIC 652E control loop set point is 78 inches. So what's going to happen is it's actually going to wait. It's not going to do anything until level rises up to 78 inches or close to it. And then it's going to start to control to keep level at 78 inches because that's what a PI control loop does. It tries to maintain at the set point you tell it. So we have a problem that arises. So that's one issue, but another problem that arises is that in between, when both valves are modulating, when the small valve isn't fully open yet and the large valve has started to open, which in this case is about between 10 and 20 gallons a minute, both of these valves are simultaneously modulating the process, and they're trying to control the same level. Well, they're going to interact with each other. Especially the large valve. As the large valve barely starts to crack open, it's going to cause major fluctuations on the small valve, and of course the small valve is going to react and so forth. You're going to end up getting some fluctuations and even oscillations. In the real example, the real world situation on this, it's pretty notable oscillations. And the graph at the bottom kind of shows illustrative, an example. I just sketched these, but it shows kind of what happens. If you look, you'll notice when it's less than 10 gallons a minute, because of the mismatch, the raw influent minus effluent values, when that mismatch is less than 10 gallons a minute, it's hanging out about 66 inches, pretty stable. When it's in between 10 and 20 gallon per minute mismatch, you get oscillations, and at some point it might reach the higher set point of 78 once, if it gets up to 20 gallons and the LIC 652E takes over, or it might actually oscillate and then drop back down. It all just depends on that mismatch. So the mismatch kind of drives the behavior. If the mismatch is greater than 20 gallons a minute, then the large valve is fully in control, and it's going to basically get this process up to 78 inches and try to keep it there pretty stable until at some point the mismatch drops down in the 10 to 20 range. You get oscillations, fluctuations, and so forth until it either returns to above 20 or below 10, at which time it either picks 66 or 78 inches and stabilizes again. I looked at this process for like a really long term, many months, and this is exactly what happened over a period of time. Stable at low set point, stable at the high set point, stable at the low, oscillations. It would fluctuate back and forth. Sometimes it would oscillate in the middle if it was at that imbalance level for a long time. But it's very easy to pick up on a long-term DCS history. Not a desirable process control, very ugly, very poor control, but it doesn't cause trips. So sadly, they don't really worry about it. They really kind of focus on things that cause trips or downtime or that they can visually make sense of easier. So one good solution that accomplishes the functional description very clearly is to use proportional only control loops, because basically what that control function described was for the small valve to start opening at 54 inches and to be full open at 78. So that, if you look here, that's a proportional response. And that's fairly easy to do. You can have two loops in this case. You could have three, four, whatever. So in this case, the big valve starts opening at 72 inches and it's full open at 84. So there's a little bit of overlap there. There could be more, there could be less. But basically, because you remove the integral function on a proportional only controller, it's not trying to seek the center point. It's going to allow it to just rise up. And as it rises, the valve is going to open more to try to accomplish the goal of getting the level down where it's supposed to be, which is really down in this area is where the thing is supposed to operate. These are actually override type controls to prevent overflows. So there's like a middle band here. So by doing that, you accomplish that. And what you do is you avoid the interactions of these two control loops or control valves. You allow them to work together, both of them pushing the level downward by discharging overboard to balance that flow out for those conditions. So in truth, I don't know the full detailed history of this scenario that I'm describing that I observed, but I know enough about the organization and I've seen enough of the loops, other loops, and other issues to have a pretty good idea of what happened here. And I think it's probably quite common across all industry. And I've seen the same kinds of problems in other facilities and organizations as well. So in this particular instance, it appears that, in not just this one, in a lot of them for this particular facility, the person's doing the actual DCS programming made some mistakes. And the reality is, most DCS programmers are geniuses. They really are. They are super, super smart, and most people have no idea what they do. So they just kind of assume that they know everything. While they may be geniuses, it doesn't mean they automatically know everything about process safety, about process control, and about the other, myriad of process details from chemistry to, electrical engineering to mechanical engineering. They're an expert at what they do, and they often have some of that exposure, but they do not always know. And this is a little bit out of the ordinary. This is not the standard thing. So what happens at this particular site, they tend to pop a generic PID block. They have kind of a standard library. They pop it in, and one of about four, they pick one of the four that seems the closest, and they're all basic blocks, and they throw them in and kind of hope they fit. It's kind of a trying to fit a square peg in a round hole sometimes. Um, then somebody has to commission it, start it, etc., and they often don't know either. So they're out there trying to find some numbers that kind of work, and they don't really know that the real solution to this is to alter the logic that was programmed. That's an extremely common problem in process control, and I can tell you companies don't want to hear that. I've been there trying to explain to them this can't do it, and had engineers, literally senior engineers, oh no, we just need different numbers. Well, it's not about the numbers, it's about the logic. um, so it's a real common problem, and it's one that hopefully this will help give some insight and enlighten people to where you can see at least enough to go, yeah, there are possibly better ways to solve this without just throwing some numbers that work, because you can throw those numbers that work in this application and it does work. It doesn't trip, it doesn't cause alarms, but in other applications at this same organization, they're suffering because of this same kind of thinking. So I just picked one that's a little more digestible in a short time frame. So basically, in this case, once everything's done, they get the system kind of running, and then they forget about this. Um, the process, if you look at the history, it's terrible. It's fluctuating. It's at two different set points. It's all over the place. Not good process control, and history shows it very clearly. But since it's not tripping the plant, let's not worry about it. That's just a mentality thing. That's a culture thing, really. And coming from the nuclear navy, we were taught, you try to make everything run right. You don't just kind of live with stuff. So that's there's a reason they do that, and there's a reason that that organization performs at a high level like it does. So they convinced me, and I'm trying to convince others. So hopefully this is helpful. If you do have questions, input, comments, feel free to reach out. Um, and I appreciate your attention. Thank you.